Okay, good afternoon. Today, let's finish up our load line analysis of the CE amplifier. So we stopped right here. We have the input characteristics and the output characteristics, right? We'll first write load line equations for the input side and then transfer them over to the output side. So first, I want to explain how it would work as an amplifier using these graphical techniques, right? So let's say you have IB. Okay, IB is the input side. IB and VB are the input voltages. Right? So again, look back at the circuit here. IB is the current that's entering the base terminal, and VB is the voltage that is being seen at the base. Okay, so VB and IB are the voltages and the currents that are going into the input side. On the output side, it's IC and VCE, and that's what's shown here in these graphs. IB, VBE, and IC, VCE. So let's say IB varies from 10 microamps to 30 microamps, okay? And all of these annotations are already available at your end. So I copied them over so we can go at a slightly faster pace. So this is a sinusoidal waveform, and IB is basically a sine wave going from 10 microamps to 30 microamps. We have applied our DC voltages, VCC and VBB, that set the bias for our operating point, right? So that operating point is fixed. It depends on the values of the components, and it depends on the values of VCC and VBB. The operating point moves in response to Vin. So if no Vin is applied, or when Vin is equal to 0, there is no AC, the operating point is fixed. It's fixed on the load line. And so on the input side, the operating point will be fixed right here, let's say. The values, of course, depend on VCC and VB. So now let's say we apply Vin of t. Vin of t is a sinusoidal waveform. It varies from 10 to 30 microamps. So 10 is right here. 30 is right here. So if I was to mark this, I would say this is 0, 10, and 30. Not quite the same, but those are just random values that I'm using for explanation purposes. So input waveform is right here. So now there are three things going on in this input waveform on the output characteristic. We have the input right here, and that input is basically IB variations. IB variation is again 10 to 30. If I take the intersection, which is these 3 points, and let's go to the left, and I move it to the left right here, I get my output IC, or the output current collector voltage. I mean collector current. IC moves in response to IB. And you can see the value of IC is almost 100 times that of IB. This is just graphically, okay? IC, of course, is beta times IB. Beta is 100. You would expect that IC would be about 100 times IB. So a small input results in a large output. Obviously, these are not to scale, but you can see IB is microamps. IC is not written here, but it would be typically in milliamps. And so again, this is not the example. This is just a random explanation, random numbers for the explanation purposes. So microamps results in milliamps of output, and the shape of the output follows the shape of the input. So that's the second thing. The third quantity, the third thing is VCE, the output voltage. Here's what happens. If you extend this line to the x-axis, we can find values for VCE, collector to emitter voltage. Okay, that's the intersection point. So if you look at the intersection point, the maximum value of the input, this is the maximum value of the input, gives you the minimum value of the output. Okay, I'll write this down here. Simply note it as max input voltage or max input gives us the lowest or the minimum value of the output voltage. And then the minimum value of the input gives us the max value of the output. Right? This is obviously 0. VC is increasing in this direction. IC is increasing in this direction. And 0, of course, means that's the center line of my output. And so again, what that means is that my waveform is 180 degrees out of phase. My small input waveform, that's AC plus DC, gives me an amplified output. And that amplified output is 180 degrees out of phase. So you get an inverted output. Inverted output. Okay. Does that make sense to everyone? And we'll perform the analysis in the next couple of slides. All right, so let's look at the example. So load line analysis of a C amplifier. Given information, VCC, the DC voltage applied to the output side, is 10 volts. VBB, the DC voltage applied to the input side, is 1.6 volts. The base resistor is 40 kilo ohms. Collector resistor is 2 kilo ohms. Okay. V in of T is 0.4 times sine 2000 pi T. That means VM or VP, peak value or the magnitude of the voltage, is 0.4 volts. Frequency is F is omega over 2 pi. So 2000 pi divided by 2 pi, you get 1 kilohertz. Frequency is irrelevant, right? The signal does not affect the frequency. Only the magnitude and the phase is affected. So this is of importance right here, 0.4. Remember EE201. V of T is VP sine omega T. VP signifies one single peak. The sinusoidal waveform, it signifies positive peak and the value of the negative peak. So our input waveform is swinging between minus 0.4 and plus 0.4. The lowest value of the input is minus 0.4. Maximum is plus 0.4. Again, this is given in the value of V in of T, but it would be up to you as an engineer to interpret that. Okay, it's not from 0 to 0.4, it's from minus 0.4 to plus 0.4. Keep that in mind. All right. On the input side, let's apply KVL. We apply KVL, we obtain an expression for IB. IB would be VBB plus V in or RB. This is something we did in last class. So VBB is 1.6. If V in is 0, meaning the crossing between positive and negative half cycle, my center line is at 40 microamps. V in goes to 0.4. IB increases to 50 microamps. V in swings negative, goes to minus 0.4. IB now goes to 30 microamps. So IB swinging between 30 and 50 microamps. Okay, you all with me so far? VBB and VCC are applied as DC biasing voltages that fixes the operating point in the middle. And then you apply an AC input. The AC input causes variations in IB, which causes variations in VB, or you can also state it vice versa. And so the base voltage is now changed. Base voltage equation is right here, VBB plus V in. And so it's 1.6 plus 0.4 minus 0.4 and then plus 0. So base voltage now swinging between 1.6 and 2 volts. So we obtain the two ends for our load line. IB is 50 and 30, and VBE is between 1.2 and 2. So you have three different load lines, one at the Q point or operating point, the other one is for the positive swing, and the third one is for the negative swing. So three different load lines results in three different intersection points. Those three intersection points are right here. At the Q point, when there is no AC input voltage, resulting IB is 25 microamps. The Y coordinates of those intersection points will later be transferred to the output. So we need to know how the output is changing due to the input, right? So we need to find the intersection point. Where is the Q point shifting along the load line? So it goes up with increasing input voltage, and it goes down with decreasing input voltage. So Q point is at 25, and it shifts or moves up to 35 for positive, shifts down to 15 for negative. All right, let's take a pause. Think over that. Let me know if you have any questions. Yes. So we derive those equations. Oh, wait, you're talking about the characteristics? Yeah, those are given. So the question being asked is if the homework problem or a quiz or an exam, what about the characteristic? They would be given. Yeah. Okay, any other questions? So far, so good. Okay, so we have our three values. Let's go to the output side. On the output side, we'll take these values, 15, 25, and 35 microamps, and we will find the characteristic that corresponds to those three values. Okay, 15, 25, and 35. Remember, the output characteristics are basically a set of data points. There is one set of data point for each IB value. Okay, each value of the input base current, you have a data set or IC as a function of VCE. Okay. So 15, 25, and 35. We find those lines and we find the intersection point at the output. By writing, excuse me, we can write a KVL expression at the output, VCC minus ICRC plus VCE is equal to 0. So going back to the circuit diagram, right here. On the output side, voltage VCC, let me get rid of all this. Voltage VCC is divided across load resistor RC and the collector emitter voltage VCE. So if I write a KVL expression, on the output side, it's simply VCC minus ICRC KVL at output gives me minus VCC, actually minus VCE minus VRC plus VCC is equal to 0. That's simply VCC is equal to ICRC plus VCE. Okay, ICRC plus VCE. So from here, I want to plot the load line. So load line coordinates. If IC is equal to 0, then or therefore VCE is equal to VCC. Standard procedure for load line, right? We want to find the two ends of the load line that intersect the X and Y axis. So you plug in X axis value equal to 0 and then Y axis value equal to 0, we find the other value. So if VCE is equal to 0, then IC is equal to VCC over RC. Right? So if IC is equal to 0, VCC is 10 volts. And so we obtain the X-axis coordinates for that load line. VCC is equal to 10 volts. And then ICC is equal to 10 divided by, what was the value for RC? 2 kilo ohms. So 10 divided by 1000, get 5 milliamps. You all with me so far? Yes? No? I will recap all of this again, so bear with me. So load line coordinates, VCC and VCC over RC. Once you have that, you plot the load line right there. Once you plot the load line, it's going to intersect your output characteristic in in every single output characteristic is intercepted, right? So there's intersection points everywhere. But we are only interested in 3. We are only interested in this, this, and this. 15, 25, and 35. Those are the only ones we are interested in. And so we take those 3 intersection points and we extend the coordinate, we extend the intersection points to the X and Y axis. Those coordinates is our solution or are our solution. And so on the left, we obtain IC values as 1.5 milliamps and 3.5 milliamps. And on the x-axis, we find VCE swings between 3 volts and 7 volts. So a small input voltage, we're applying a small AC voltage that only goes from minus 0.4 to plus 0.4, basically 400 millivolts. And that results in an output voltage of 4 volts, swing of 4 volts. Okay. All right, so let's take a pause, and then I will summarize everything again. Any questions? No questions? Everybody understands everything. I don't need to summarize. Okay. All right, let's summarize from the beginning. So we have an amplifier circuit. We are applying DC biasing voltages, VBB and VCC, and we are given the values of RB and RC. We're also given the plots. So the plot in blue, or the plots that in blue, on the left is the input characteristic, on the right is the output characteristic. Okay. We wish to perform load line analysis in order to determine the output for any given input AC signal. Okay. In order to do so, we will plot load lines. To plot the load line, we need the coordinates for the x-axis and the y-axis. So we apply KVL on the input side, and we apply KVL on the output side. By applying KVL on the input side, we can plot this load line right here on the input characteristic. By applying KVL on the output side, we can plot this load line on the output characteristic. The load line procedure is not new. It's the same that we did for the diode. It's the same we did for the Zener diode. Apply KVL, obtain X and Y coordinates, and you plot the line. The intersection of the line is our solution. Let's say we do not apply any AC voltage. Okay, let's say we do not apply any AC voltage. Then our intersection point on the input side is here. That's our Q point, VSN point. We take that and we bring it to the output side. Because the coordinates on the input side tell us where the intersection point, or which intersection point we must take here on the output side. That makes sense? Here, let's say our intersection point is 10 microamps. Then on the output side, it would be here. Because the load line on the output is intersecting in, let's see, 1, 2, 3, 4, 5 different spots. So we need to find the one that is caused due to the input being applied. If no input is being applied, then it's a Q point. It will be somewhere in the middle, depending on the design of our circuit. But now we apply an AC input. When an AC input is applied, this Q point swings up and it swings down, depending on the form and value of the AC input. And because it shifts up and down, then the output also shifts up or down. And thus we have 3 intersection points, one at 0, one at minimum, one at maximum. And so we take those 3 from the input side, we calculate those by applying KVL on the input side, right? So we obtain these three intersection points on the input side. We obtain values for IB. And from those values, we go to the output load line and we select those three plots. Again, the output has multiple intersection points right here. We don't know which ones to take, but those depend on our input values. Okay, there are, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 different intersection points. Depending on the design of our amplifier, depending on the value of the input that we're applying, our output could be anywhere along this load line. Okay, right now, of course, for explanation purposes and for instruction purposes, we are choosing nice values that are in the middle of the active region. And because it's in the middle of the active region, we get an amplified waveform that is an intact replica of the input. Amplified, but still an exact replica of the input. Does that make sense? And that's how we would perform a load line analysis of a CE amplifier. Everybody would be able to do this on the quiz on Monday. There's a homework that's due today. That's for the Friday quiz. And there's a homework due on Sunday. That would be for the Monday quiz. So if you plot this, as I was saying, input swings between 400 and minus 400 millivolts. The scales are different, right? V in is less than 1 volt. Even though the waveform looks, even though the waveform on the right looks smaller, the scale is different. Okay. 180 degrees out of phase. It's an amplified output. That's how it works as an amplifier. Okay. It's basically taking the DC voltage at the output, which is VCC, and it is giving the shape of the input signal V in to that VCC biasing voltage. Okay. So again, if you're not applying any input, you would simply get the output as 5 volts VCE. Yes. Yes. The blue plot lines, right? Yes. This one, yeah, that's on the input side for the base. So it's a base emitter. So it's a function of IB. Sorry, IB as a function of VBE. So it's basically a forward bias PN junction diode. Hence, it looks like this. So that's the input side, and the one on the right is the output side. But it's an amplified output, 180 degrees out of phase. So if your VCC is like 20 volts, you can get an output even larger than 7 volts, right? Depending on what voltage we're applying and depending on the biasing conditions. Now, however, if you drive the transistor into an extreme, meaning if your input is large, what happens then? Remember, we are applying plus 4 volts. Sorry, not plus 4, 0.4. This is just 0.4 volts. And we get a swing of 2 volts. So 0.4 volts is increased to 2 volts. So instead of 0.4 volts, if you apply like 1 volt or 2 volts, what happens to the output? Well, the output would be far too large. But energy does not come from thin air. Again, remember, I just said, right? It modulates VCC, the output voltage, and gives it the shape of your input signal. So if the input is very large, the output goes correspondingly larger, but the transistor is not going to provide extra energy beyond what it receives from VCC. So it drives the transistor into saturation, and at the top end, the output gets clipped off. And if that happens at the negative end, it's get clipped off, and it drives it into cutoff. And this appears as a distortion. If this was an audio signal and you increase the volume far beyond what your amplifier or your speakers can handle, it will seem as if the speaker cone is being torn apart, right? And so that appears as distortion. And let's go back to the load line, and I can show you how that would work. So if the Q point was in the center, we get a perfectly amplified replica of the input waveform. However, if now your Q point is somewhere here at the top, what happens then? Your output is now beyond the capabilities of the waveform. So the top half of the waveform is now clipped off. You've driven the transistor into saturation on the left. Remember, this is saturation region. So if your input is here, right there, your output would be somewhere here. So it'd be something like this. Something like this. But transistor cannot give more than this waveform. So let me draw this out in a way that would make sense. Let's say the Q point or the input is here. And then my output would appear something like this. Yes. Yes. Question being asked was, in this example, it would only be clipped on one end. The answer is yes, only one end. And then if the same Q point was somewhere over here, well, then the other end would get clipped off. So this end would get clipped off. So you're driving the transistor into cutoff. So even though we bias a transistor to work in the active region, everything depends also. So there's two things going on. V in could be large enough that the output exceeds both positive and the negative end. So it gets clipped off at both ends. But if we don't bias a circuit correctly, meaning the values of VCC, VBB, and the resistors in there, RB and RC, would move the Q point either up or down the load line. So Q point wouldn't be in the center. Q point would be somewhere here or be somewhere here. That is a result of DC biasing, not V in, not the AC input voltage. So that would be an incorrect biasing or a poorly designed biasing circuit. Okay. And the second would be if V in was large or larger than the capacity of that or the gain capacity of that transistor amplifier circuit. And again, distortion would result. Make sense? Yes. Yes and no. So the question being asked is, what do I mean by when a transistor enters into saturation? So DC bias remains as it is, but um, because the circuit was poorly designed, it is still in the active region. But when V in arrives, it now changes the biasing conditions. Q point is now shifted up or down. Okay, so DC bias remains constant, but again, that DC bias plus the AC voltage that's arriving is shifting the Q point up or down the load line. So in a way, yes, we can state, yes, the bias of the transistor is changing. But technically, we would say DC bias simply means the DC voltage that's being applied. All right, other questions? Okay. So 180 degrees out of phase is, and I typically bring this example up in my 201 classes. There are other amplifier circuits that are designed specifically not to provide gain, but just to flip it 180 degrees, to flip the signal 180 degrees. One of the most common examples in real life is noise cancellation. The noise cancellation headphones or noise cancellation technology by itself, anywhere you apply that, is simply capturing the ambient noise with a microphone, flipping it or switching it by 180 degrees out of phase, and then adding it with the originally captured signal. So if you capture this with a microphone, then you flip it 180 degrees. Obviously, this is not exactly to scale. What is the resulting output? 0, because the phase is 0. So noise cancellation. Every single phone that we ever used, even before the smartphone era or smart device era, always has a tiny, small opening right next to the speaker. And so that's to prevent any ambient noise from interfering with the conversation. And so then they extended that technology and created noise canceling headphones. All right. So the one of the downsides of the single bias circuit that we saw with a single resistor is that it is heavily dependent on the transistor itself. If the transistor beta is different or vastly different from one device to the next, then the biasing conditions will change just simply based on that. And so there is a very popular biasing design that is used that is known as the 4-resistor bias. The 4-resistor bias is so called because you use 4 resistors in that circuit. One at the collector, one at the emitter, and 2 at the base. Okay, and 2 at the base. So this creates a voltage divider network between the 2 base resistors. Hence, this is also known as a voltage divider bias. Okay, voltage divider bias. And because there are 2 resistors that are going in there, we are going to use or we are going to call upon Messrs. Thevenin and Norton. We need to go from this circuit to this circuit. Right? We need one single RB and one single value of VBB. So we need to reduce R1 and R2, and then of course VCC into VBB and RB. And we do that by determining the Thevenin equivalent network as seen by the base emitter junction. Which means we will split up a circuit right here because we want to find the Thevenin circuit as seen from the perspective of the base emitter junction. It is still the same circuit, it's just redrawn in a different way. Okay. You have plus VCC here. Simply means you're applying VCC between these two terminals. And then we are redrawing it separately so we can show that VCC is also applied to R1 and R2. From this point on, it is simple voltage divider network. We want to find, this is the base, this is the emitter. So we want to find the Thevenin equivalent circuit as seen from the perspective of the base emitter junction. So we simply find VTH as VCC times R2 over R1 plus R2. This is voltage division. Voltage division. Two series resistors dividing a supply voltage. So VCC is split between R1 and R2. And then whatever value drops across R2 is the VBB that is going into the base terminal. Okay. And RB would simply cause R1 and R2 to be in parallel. To find RB, everyone remember this? Maybe not. We replace all voltage sources with a short circuit, and we find REQ between our terminals of analysis. And because voltage source is replaced with a short circuit, that brings R1 in parallel with R2. And that's how you find RB. Okay. But what that does is it gives us this kind of circuit. And in this circuit, we can use a model for the collector current. Collector current is beta times IB. And once it reaches, once it curves in, it behaves like a constant current source. And because it is dependent on IB, we can model it as a dependent current source with a value of beta times IB. So now we apply KVL at the input and the output side. We obtain this expression. Okay. IE is the sum of IC and IB. IC is beta times IB. So we can rewrite IE as beta plus 1 times IB. From there, we rearrange the terms and we want to determine what our input current is going to be. Okay, we want to determine what the input current is going to be. So IB is VB minus VBE divided by RB plus beta plus 1 RE. There is a point to this. Remember, I made a statement saying that the output is highly dependent on the beta of the transistor. So if we take one transistor out and we plug another transistor in there, even though it's exactly the same model, perhaps manufactured at the same time on the same substrate, the beta could be highly different. One of them could be 100, the other could be 110, 120. So we design circuits so that it is independent of the beta. And that's where this is going. So we have this equation. IB is VB minus VBE. On the output side, we obtain VCE is VCC minus RC. It's the same standard equation, except now we also have a emitter resistor And so there's an additional voltage drop minus IE times RE. Otherwise, it's the same equation that we saw earlier. When we solve this, if you want to determine the output of the circuit for beta is 100 and beta is 300, we can find it by first finding the Thevenin circuit, RB and VB. So we find RB, we find VBB, the base voltage, plug the values into the equation for IB, and determine that IB is 41.2 microamps for a beta of 100. Okay, for a beta of 100, IB is 41.2 microamps. If you take that transistor out and you plug in the exact same transistor, but now beta is 300, IB is reduced. Excuse me. IB is only 14.1 microamps. Again, same equation, different betas, 100 versus 300 gives you two different values of IB for those two different transistors. But look at the effect on the output current. The output current is still within the same range, 4.12 milliamps and 4.24 milliamps, difference of about 0.10 milliamps or 0.12. Okay, so there's not much difference with using two different transistors with two different betas. And that is the primary application, or why this voltage divider bias is very popular. So the 4 resistor bias or the voltage divider bias is very popular because the circuit can perform independent of the transistor beta. On the output side, VCE also remains near, well, I wouldn't say constant, but also remains within the same region. So 6.72 volts versus 6.51. Not much variation. It varies, but not a lot. And of course, this is an extreme example. You have two transistors, one with beta 100, another with 300. Okay. It does happen that the same exact model transistor might have variations this large, but typically it would be within like 100, 125, or 100, 150. And not too far off from there. And so you plug in 150 in there, it'll be even closer than these values. So review these. And now we rush through a little bit because I need to pick up the pace a little bit. But review these slides, review the lecture recording, work on the homework. If you get stuck somewhere, send me an email, get in touch with me. I'll be available over the weekend also. Okay. Let's see, 58. And well, that's the end of chapter 2. So we'll begin op amps on Monday. Remember, Friday quiz today and Monday quiz coming up on Monday. And yeah, that's about it. I'll wish you a good weekend and I'll see you all on Monday. Oh, I forgot these. I bought some items for show and tell. These are 8-inch silicon wafers. I wouldn't do that. These are slightly thick. It's like not even a millimeter. But if I drop it even from this height, they could break and shatter. And these were processed and polished, but you can still handle them. It's fine. So I won't give you all of them, but and these are actual class wafers fabricated by students here at Cal Poly. Okay. And I can't believe I forgot to say that, but the director of the clean room is Dr. Hans Meyer. He is a mechanical engineer. So if you get a chance, stop by Engineering 3, the materials engineering department up on the 2nd floor, and you'd be able to walk by the clean room. It's a restricted facility, so you can't just enter in. But if you do take the class, you can go in and you're able to work on these kind of silicon wafers. So Dr. Hans Meyer, he is the director of the clean room. Dr. Benjamin Hawkins from BMed, he is the assistant director. And we teach a class every single winter, where students can go into the lab and build their own microchip devices. All three of us take one section each of the lab, and the theory lecture is taught by Ben Hawkins. Okay, but it's only offered once a year in the winter quarter. So if you're still around here next year, you might consider taking that class. All right.